Hi, I am Mahmut Kağan Akkuş and I am from Industrial Engineering Department and my ID is 22502270 and I am doing my Physics Individual Lab project for Physics 101 and I am investigating the effect of temperature difference, wear and surface type on the kinetic friction coefficient. For physical background, the kinetic friction force is given by kinetic friction equals mu k times normal force. In this project, I did not measure mu k directly. Instead, I measured the average pulling force and calculated the acceleration using video timing. So I used F average minus m multiplied by a divided by mg. Temperature, surface roughness, and wear all influence friction at the microscopic level. Higher temperature weakens adhesion, while wear can either smooth or roughen a surface depending on the material. The block itself has a mass of 0.056 kg and I added the 3 additional 0.1 kg masses, giving a total mass of 0.356 kg. Next, I put the block over the glass surface at room temperature, recording the pulling force and the time over a 0.40 meter distance. I repeated the same procedure on the aluminium surface again. To investigate the temperature effects, I cooled the glass surface to around 10 degrees using a frozen PET bottle and performed the pull again. Then I heated the glass surface to approximately 55 degrees using a hot water bag and repeated the pull. These three temperature points, 10 degree, 25 degree and 55 degree, allowed me to create a UK temperature graph. To study the effect of wear, I performed 50 repeated pulls on the aluminium surface as shown here. After these repeated pulls, I measured mu k on the worn aluminium surface. I also repeated the same wear procedure for the glass surface. And finally, I measured mu k for the worn glass surface as well. Using all measured mu k values, I created mu k temperature graphs for both surfaces and applied best fit lines. The slopes of these lines represents the temperature sensitivity coefficient. The results shows glass has a larger B value, meaning it's much more sensitive to temperature changes. Aluminium has a smaller B, meaning temperature affects it less strongly. Next, I created wear graphs plotting mu k versus the number of pulls at room temperature. The slopes of these lines represents the wear coefficient C. The results were glass has a very small C value, meaning wear has almost no effect. Aluminium has a C value about 5 times larger, meaning wear significantly reduces mu k. Comparing both effects, for glass, temperature is clearly the dominant factor. For aluminium, temperature and wear are both important and have comparable magnitudes. Additionally, at all temperatures, for the surface type effect, glass produced higher mu k values than aluminium, which aligns with stronger adhesion typical for glass surfaces. There were several sources of error. The block was pulled by hand, so the applied force was not perfectly constant, and the acceleration we calculated represents an average value. Another important source of error is that the spring dynamometer was not always completely horizontal during the pulls. Surface temperature fluctuations and video-based timing uncertainties also contributed to minor deviations. Despite these limitations, the overall trends remained clear and consistent. In conclusion, this experiment successfully demonstrated how temperature, wear, and surface type influence kinetic friction. The B and C coefficients obtained from the best fit lines allowed a clear quantitative comparison. Thank you for watching.